Okay, sports fans, let us go and get into a review of titration. We have 4 types of titration we want to talk about. Let's begin with strong acid by a strong base. So let's say we take 100 milliliters of HCl, and we're going to titrate. And what kind of HCl is that? We'll call it 0.1 molar HCl, and we're going to titrate that by 0.2 molar NaOH. Good. So that's what we're going to do. Now, how do we figure out the pH for all of these? Initially, we only have HCl. So my pH, my concentration of hydronium is going to equal the concentration of my HCl. And so I'm going to take pH, which is equal to the negative log of my strong acid concentration. There you go. That's the initial. Before the equivalence point. So let's say we have, let's add 30 mLs of NaOH, and I'll tell you how to get the equivalence point soon enough. So we add 30 mLs of NaOH to this. So what we need to do is figure out how many moles of acid, which is hydronium, right, remain. And how do I get how many moles of acid remain? I'm going to take my initial moles, so 0.100 liters times 0.1 molar. And this is my initial concentration, well, excuse me, initial moles of my H plus. Those are my initial moles of H plus, minus moles of OH added, minus OH added. And so in this case, I'm going to take 0.030 liters times 0.2 molar, okay? And that'll give me my moles of hydronium, 0.1 times 0.1 minus 0.03 times 0.2, and I get 0.004 moles of hydronium remaining. But I need to have concentration, so then I need to get the concentration of my hydronium remaining, and that's going to equal to my moles, 0.004 moles, divided by total volume. And what's my total volume? 0.1 plus 0, nope, 0.1 plus 0.03 liters. Got it? I'm going to take my liters here and my liters here, add them together, and that'll give me my concentration divided by 0.103. Nope, not 0.103. How about 0.004 divided by 0.13? And I get 0.0307 molar. And then I'm going to take the negative log of that, because this is my hydronium concentration, and then I will take the log to get the negative log to get my pH at the equivalence point. So what does it mean at the equivalence point? That means my moles of hydronium equal my moles of hydroxide. So how do I figure that out? Well, how many moles of hydronium did I start with? Figure out your original moles of acid. So moles of acid original, which is going to equal moles of hydroxide original, and then work from there. So how many moles did I have originally? I had zinc, what? Please work. 0.1 times 0.1, so I have 0.1 times 0.1, which is equal to 0.1 times 0.1 is 0.01 moles of hydronium, which is equal to the moles of hydroxide. Good. And then from there, I want to go to moles of my base. In this case, since I have NaOH, it's a 1-to-1 ratio. So this then also equals my 0.01 moles of sodium hydroxide. And then how do I get volume? Well, molarity is equal to what? Moles per liter. So that means liters equal moles per molarity. I have 0.01 moles, and I have 0.2 molar. So divide that by 0.2, and I get 0.050 liters. So 50 milliliters is my equivalence point. That's how I determine that, and I'll use that same process for determining it with all acids and bases. And for strong acid, strong acid by a strong base, the equivalence point is 7. Good. After that, what do I have here? Well, here I have leftover base. So what am I going to do? I'm going to figure out how much OH remains, and that's going to be equal to my OH added minus original hydronium. Original, good. So what am I going to do in this case? So something after 50, so let's say 70, let's just say 70 mils because it's after. So I'm going to take 0.070 liters times 0.2 minus, I started off with what, 100? 100 times, that's nice, 100 times 0.1, and so what do I have? 0.07 times 0.2 minus 0.1 times 0.1, and I have 0.004 moles of OH minus remaining. And once again, I don't want moles, I want concentration. So that means my concentration of hydroxide remaining equals 0.004 moles divided by total volume. And now my total volume is 0.070 liters plus 0.100, so that's equal to divided by 0.17, and I get 0.0235 molar. But what is this? This is OH minus concentration. So that means from this, I can get POH, and then I have to go from POH to pH. Got it? That's all there is to an strong acid by a strong base. Now, what does that curve look like? Strong acid by a strong base. We're going to start off with a very low pH. The slope of the line is going to be pretty flat here, and then I'm going to have a rapid increase and then another flat zone. The rapid increase is indicative of a strong acid by a strong base. Now, my equivalence point is right where? Right at 7. Now, what kind of indicators can I use? Phenolphthalein is a good indicator, as well as methyl red. And you want those indicators to lie somewhere within that sharp increase. All right, great. Next, strong base by strong acid. Same thing we did. And I'm not gonna redo the numbers, but it's just the opposite of what we've did. What do we start with initially? Well, I only have base. And so what do I want? I want to get moles of hydroxide over volume of hydroxide, and that'll give me my concentration of hydroxide, right? And usually, you know, most of the time this is going to equal, most of the time, it's going to equal the concentration of my strong base. We do have to watch out in case I have something like BaOH2, right? If I have barium hydroxide, then my OH is going to be 2 times my strong base concentration. But watch that. And then from this, I can get my POH. And remember, we're not asking for POH here. We're usually asking for pH, so convert from POH to pH, right? 14 minus blank, 14 minus POH will give me my pH. Equivalence point, same thing we did before. We want to figure out how many moles of hydroxide we started with, and then from that we get moles of acid, hydronium, and then I'm going to take my moles of acid and divide that by my molarity of my acid, and that'll give me my volume at EQ. Got it? Okay, before the reaction, same thing we did before. We want to know hydroxide remaining. And how am I going to get that? I'm going to take my hydroxide original minus acid added. So I'm just going to figure out how many moles of my acid were added. So I'm going to take volume of my weak acid times the molarity of my weak acid. That'll tell me how much acid was added. Got it? Not weak acid, strong acid. Sorry. Good, strong acid. And then I'm going to take this, can't do it this way. We got to start with moles, right? Sorry. We need OH moles remaining, which is moles of OH original minus moles of strong acid added. Then once I do that, I'm going to get my concentration of hydroxide remaining, which is equal to moles of OH remaining over total volume. And from that, I'm going to get my POH, and from that, I'm going to get my pH. At equivalence point, it's 7. And after the equivalence point, I will want to find moles of my strong acid excess. So I'm going to take the moles of strong acid added minus moles of OH minus original. Excuse me, how do I get this? I'm just going to take my volume times my molarity. The volume added, the volume of my acid added times the molarity, and this is my original stuff, right? And then once I have the moles of SA excess, I want to get my concentration of my strong acid excess. So I'm going to take my moles of strong acid excess over total volume. And what is total volume? The volume of my strong acid added and the volume of my hydroxide to begin with. From this is going to be concentration of hydronium. So this directly gives me what? pH. There we go. Now what does that look like? The curve is essentially the opposite of what we have here. We're going to start off high, and we're going to have a slow kind of downward for a while, and then voink, like that, and then like that. And my equivalence point is still going to be 7, and really phenolphthalein and methyl red should both be good indicators for you. To figure out if it's an strong acid, strong base, which one is titrated by which one, see where you start. If I start up high, that means I start with a base. If I start down low, I start with an acid. Great. Now the hard ones. Let's talk about a weak acid by a strong base. And let's go with, let's say I have 0.1 molar acetic acid. Let's do this right. Let me slow down a little and get this right. Let's have 0.1 molar acetic acid. And how much? Let's say we have 100 milliliters, which is 0.1 liters. So let's say I have 0.1 liter of 0.1 molar acetic acid. And to that, I'm going to titrate it with 0.2 molar NaOH. Good. What do I have initially? Initially, I have a weak acid. So what am I going to do? It means I'm going to have to use my ice box and do all the stuff and come up with what? The concentration of my hydronium is equal to the square root of my initial concentration times Ka. So in this case, it would be the square root of 0.1, because that's my initial concentration, times my Ka of 1.8 times 10 to the minus fifth. There we go. And where does this come from? This comes from ice, right? This comes out of ice. We're assuming X is much, much smaller than my initial concentration. Great. As I start adding strong base, what do I make? I end up making a buffer. Good. And for a buffer solution, how do we solve buffer solutions? I tend to like using Henderson-Hasselbalch. Henderson-Hasselbalch, which says that my pH equals pKa plus the log of the concentration of my conjugate base over the concentration of my weak acid. Now, this is not the weak acid original. This is the weak acid which remains. Okay, now how do I figure this stuff out? How do I figure out the concentration of my conjugate base? Here's the deal. My weak acid is going to react with my hydroxide, and it will form what? Well, it's going to form water plus my conjugate, right? So that means every mole of strong base that I add is transformed into weak acid. And every mole of hydroxide I add removes some of my original weak acid. So what am I going to do? I'm going to need to have moles of weak acid remaining. And how am I going to get that? I'm going to take my original moles of weak acid minus moles of hydroxide added. Got it? Good. And then I need to have my moles of A minus, my conjugate, which is formed, and that's going to be what? Same thing. Well, no, it's not. It's going to be equal to just the moles of OH minus added. Got it? And from these two, I could put them over my volume, but in this case, since this is concentration over concentration, my volumes cancel. So I could directly go from here, moles of weak acid right here and moles of A minus here, and I don't need to convert them to concentrations because this is a fraction and the liters will cancel. And so that's the way we get this. Good. At the equivalence point. Okay, we're going to get the equivalence point in the same way we got before, right? And that is I need to get my moles of weak acid original, and so that will equal moles of hydroxide. And then from there, I want to convert to moles of my strong base. Usually that's 1 to 1. If I'm using sodium hydroxide, that's going to be 1 to 1. And then I want to get volume of my strong base, which will be equal to the moles of my strong base over the molarity, right? So that's how I get my number. That's how I get my liters of strong base necessary to reach the equivalence point. Good. Now, at the equivalence point is where the fun really begins, right? Because what do I have here? At the equivalence point, I no longer have any weak acid. I don't have excess strong base. So what is it that I have? I have conjugate. I have the conjugate of my weak acid. And so what do I need to do? Well, the conjugate of a weak acid is a weak base. That means I'm going to use my concentration of hydroxide is equal to the square root of my initial concentration of my weak base times my Kb. Well, the first problem is we're not given a Kb. So I have to get the Kb. In this case, we're using acetic acid, so that means the Kb of acetate would be equal to what? Kw over the Ka of my acetic acid. Good. So that's how I can get my Kb, which goes right in here. How do I get my original concentration of A minus? Well, I'm going to get moles of A minus, which is equal to what? In this case, moles of OH added, which should be also equal to the moles of my weak acid to begin with. But this time I need to get my concentration. It's not like Henderson-Hasselbalch. I don't have a fraction here, so I need to get my moles of weak base, conjugate base, molarity. So I'm going to take the moles of A minus and divide it by total volume, and that means the amount of weak acid, the volume of my weak acid, and the volume of my strong base added. Good. And be careful here. What does this produce? This produces OH minus, so that means out of this I get POH, and you need to still convert that to pH. Whew, mama. Okay, after the M point, what do we have? We have two things really. We have excess strong base, and we have conjugate base. But this guy overwhelms this guy, so we ignore him. All we have to do is figure out the concentration of hydroxide excess. So where do we start with that? We take moles of hydroxide excess, which is equal to moles of hydroxide added minus the moles of my weak acid that I began with. Then I'm going to take this moles of hydroxide excess, divide it by total volume, and that will give me concentration of hydroxide. From there I can get POH, and from there I can get pH. Whew, mama. Good. So there you have it. That's what we do with weak acid by a strong base. Here's a typical chart. Let's compare the differences. Number one, what's very important to understand is when I have a weak acid by a conjugate base at the equivalence point, I have a conjugate base, meaning my pH at the equivalence point should be in the high sevens, closer to 8, 8, 9, 10 range. Got it? I have a gradual slope increase here. And why is that? Because this is a buffer region, right? And what do buffers do? Buffers limit the change in pH. Good. And then finally at the end, I have essentially only strong base. And so you have a flat curve there. What's a suitable indicator here? Methyl red is certainly not a suitable indicator. Look at the methyl red is changing way back here. It's not going to be, it's much more likely that phenolphthalein will be a good indicator. But you may have to look at if on the AP exam, they may give you the curve and you just analyze the curve and choose an indicator that turns entirely within the vertical area. Got it? Okay. Finally, weak base by strong acid, everything we just talked about in reverse. First here, I have only a weak base, so my hydroxide concentration is going to end up being the square root of my weak base initial concentration times Kb, and then I want to convert that to pH. Before the equivalence point, what do I have? I have a buffer, but this time the buffer is going to be this buffer is going to be based on the weak base, so POH is equal to PKB plus the log of my conjugate acid over the weak base remaining. Got it? So good. I need to get the moles of my conjugate acid, and so the moles of my conjugate acid are going to be equal to the moles of strong acid added. Because once again, what do we have here? I have weak base plus my strong acid is going to form my weak acid plus water. Got it? My conjugate acid. So I have moles of strong acid added. How do I get my moles of weak base remaining? Well, that's going to be my moles of weak base original minus moles of strong acid added. And that'll give me my moles of weak base remaining. And then I need my concentration of, oh no, I don't. Since these are concentration over concentration, my volume cancels. I can plug that in there, plug this in here. I will get POH, and from my POH, I can get my pH. At the equivalence point, same thing. We have to get, again, moles of my weak base equal moles of my strong acid. I can get this from my original number, right, where I have molarity times my liters. Once I have moles of my strong acid, I can get liters of my strong acid by taking moles of strong acid over my molarity. Good. Now, what do I have at the equivalence point? I have a conjugate acid is what I have. And so that means my hydronium concentration is equal to the square root of my conjugate acid concentration times Ka. Okay? Good. And how do I get my Ka, though? Once again, I'm going to have to say that my Ka of my conjugate acid is going to be equal to Kw over Kb of my weak base. Got it? So I have to take my weak base from the base given to me here, get my conjugate acid, plug that in here. How do I get my conjugate acid concentration? Well, I'm going to take my moles of conjugate acid, and that's equal to the moles of my weak base original, which is equal to the moles of my strong acid added. And then I'm going to take that and I need to get my concentration of the conjugate acid, which is the moles of my conjugate acid divided by total volume. Once I have that, I can plug that in to here and I will get that. Now, after my equivalence point, what do I have? After the equivalence point, I have excess strong acid. That's all we really care about. There is, of course, my weak acid, the conjugate acid, but the pH is driven predominantly by the excess strong acid. So what are we going to do? We need to have moles of strong acid excess, which is equal to my moles of strong acid added minus moles of weak base that we started with, original, and then I'm going to I need to get concentration of my strong acid excess, which is equal to what? Moles of my strong acid excess over my total volume. Good. And from that, this will give me my concentration of hydronium, and from my concentration of hydronium, I can get my pH. And this is what that chart looks like. Got it? As you can see, phenolphthalein is usually not a proper indicator for a weak base by strong acid. Methyl red usually is, and everything is switched around. At the equilibrium, at the equivalence point, what do I have? I said I have a conjugate acid. So that means I should expect my pH to be less than 7. Good. And I'm going to have this kind of slope here because why? What do I have there? I have a buffer solution. Great. One other thing I should probably bring up about titrations, right? Is that if I get a curve and I find the equivalence point, come down here, find the volume, one half of this volume will be the ideal buffer. And the ideal buffer means that my conjugate, my weak acid concentration equals my conjugate acid concentration, or my weak base concentration, whichever the buffer starts with, is equal to my conjugate acid concentration. That is my ideal buffer. And in that case, then the pH equals the pKa, right? So here is at this point, I have equal concentrations of conjugates and weak acid, weak base. And so this pH then not only is pH, that is my pKa. Remember that, guys? I think that'll do it now. If you have any questions, ask me later.